Assalamu alaikum everyone. My name is Ahmad Riaz and today we will be discussing about the optimal passing patterns detection using temporal subgraph isomorphism. We will consider the player of football as node and their pass as an edge. In the start of the game, player passes the football to each other. A pattern of edges is created while at the start and at the end of the game, the pattern will be different. Mean pattern is changing dynamically. For identifying optimal passing patterns using temporal subgraph isomorphism for football team, we use the solution proposed by Oberoi and his team. In their research, Oberoi and his team addresses the challenges of detecting dynamic patterns within dynamic graphs through subgraph isomorphism. Dynamic graphs are used extensively to model complex systems that change over time, like social networks or biological systems. Unlike static graphs, these graphs evolve, making detection of recurring patterns within them crucial, yet computationally challenging. He proposes a novel method to accurately and efficiently identify these patterns by handling the graphs as sequences of snapshots which reflect changes over discrete time intervals. Previous approaches primarily focused on static patterns within dynamic graphs or used integrated models time-stamped edges to analyze temporal changes. Oberon's team diverges by introducing a snapshot-based model where each snapshot represents a static state of graph at a particular time. The pair model involves checking each snapshot sequentially as previous patterns, which allows for a more accurate analysis of changes over time. Unlike the aggregated approach that might overlook dynamics and his team benchmark their algorithm against two existing state-of-the-art algorithms using real-world datasets, which include telecommunication and bioinformatics networks. They provide empirical evidence showing that their algorithm not only performs competitively in terms of execution time, but also excels in scenarios where dynamic graphs cannot be suitably represented by aggregated models. This makes it particularly effective in applications where temporal precision and snapshot integrity are critical. So, hi everyone, my name is Muhammad Hassan, and I will be telling you about the overall snapshot based approach. So, first of all, which algorithm it chooses? It chooses the VF3 algorithm. What is the real secret behind the VF3 algorithm? So, it takes multiple snapshots at different timestamps and then merges to get dynamic patterns. How do it get the dynamic patterns by creating subgraphs and then analyzing them? So how can it get so accurate? The real reason behind its accuracy is the chronological order of the events. It takes snapshots and then merges them or analyzes them to get the subgraphs, and in the end, the end result it produces is the dynamic patterns. So let me tell you about the evaluation engines this algorithm. So the input it uses is the real-time data set. Like a live football match is happening and it gets the data from the live match and then analyzes and according to the algorithm and performs the computations and gives the results. And in specific cases, it performs quite well, more than other algorithms. Let's get back to the real life applications of this Oberoi's algorithm or the TF3 algorithm. It's used in email communication and social networks. Let's discuss the input and output of Oberoi's code. So the input it uses is the pattern graph being the first one, and the second one it gets the input as the target graph representing the dynamic network where you are searching for the pattern. And after all those computations and the algorithm gives it, it produces result as the occurrences of the pattern in the target graph along with the corresponding. timestamps in the other relevant information. So it gives everything to you in the result. Let's discuss the input and output directly. So here the tree is simply the number of nodes, or you can say number of points in a football field. 0, 1, and 2 being the indexes, and the V1, R4, and L5 being the names of those nodes. What is the 2 here? The 2 represents the number of edges getting out of the index 0. And same goes for here. It goes from 0 to 1 and 0 to 2. And the other two nodes, there is no edge getting out of them. So what is the output of this? It tells us the number of solutions we can get. It is only one, as you can see here, and the time it takes is 0.002. So it's literally quite efficient algorithm for us. That's all from our side, and thank you so much, everyone.